As an exercise, finding the solutions to this equation as a Diophantine equation, which simply means finding values of x and y which are integers. Obviously it's a linear equation, and a linear equation is going to have an infinite set of solutions. Well, that's going down the way. But where are the integral solutions to it? Does every straight line have to have integral solutions somewhere? Well, every straight line, when you draw it, pass exactly through the grid points at certain places? And the answer is no. If the greatest common divisor, if the biggest number that divides into these two doesn't also divide into this, then there'll be no integral solutions. If there are, then the way to find them is by using this Euclidean algorithm to arrive at a pair of values and then find the general solution to this Diophantine equation. I know when you first see this Euclidean algorithm you think, what's this wee bunch of numbers? You're just playing about with them to get some number at the end, which maybe you could have got some other way. No, the purpose of that is to arrive at the solutions to linear Diophantine equations. And the way the Euclidean algorithm works is just from the basic division principle, which is this. If you've got two numbers a and b, where a is greater than b, then that means that a can be expressed as some multiple of b with some remainder left over, where, significantly, this remainder must be less than b. In other words, b must be greater than r. Those aren't just random letters. Q is for quotient, the number of times it divides in, r is for the remainder. But because you have this, because the remainder has to be less than the number that you were dividing by, that means that since that's greater than that, you can do it again. You could start again with b and r. You can start again with these two numbers. And then find some number that multiplies it plus some remainder which will be left over, which necessarily must be less than this, and then once again you've got a number greater than another number, so you can reapply this division principle so that you have an algorithm. A process continues until it terminates when the remainder is 0. Plus, what is the greatest number? Right, got a calculator. So how many times does that go in? What number does multiply this? So you would just divide it in. 195 divided by 42, and you get 4.64 and so on. So it does 4 times it plus some number left over. To find that number from your 4.64 decimal and so on, take away the 4, leaves the decimal part, re-multiply by that 42 which you divided by, and you get 27. So that'd be the first line. Now necessarily 42's got to be greater than 27, so you can repeat the process. 42 must be something times 27. And it does. That's just 1 times 27 with 15 left over. Repeat the process. If 27 is greater than 15, that means that 27 can be expressed as some multiple of 15. Again, it's only 1 times it with 12 left over. Same process again. 15 is greater than 12, so 15 can be expressed as a multiple of 12. It's just that initial process. Again, that's just 1 times it, with 3 left over. And then finally, 12 can be expressed as exactly 4 times 3. That means 3 divides in exactly. So that means the greatest common divisor, the highest common factor of these two numbers is 3. Just to mention about the greatest common divisor. Since 3 obviously divides 3, and 3 divides into 12 because it goes 4 times, 3 divides both of those. Now since 3 divides both of those, then it must divide anything that's composed of it, must divide the 15. And since 3 divides 12 and 15, it must divide 27. And since 15 and 27 were both divisible by 3, it must divide 42. And since 27 and 42 are divisible by 3, it means it must also divide 195, which means 3 divides both 42 and 195. But does that mean it's the greatest common divisor, highest common factor? Well, the other way around. If 195 and 42 divide by some number, don't know what it is, it may even just be 1, just some number, call it m, then 27 must also divide by that number. If 27 and 42 divide by whatever number that is, then that must also divide by it. Just think of those two going together. They'd be a common factor with that number multiplying. That would also have to divide by it. If whatever that number is divides those two, then it must also divide 12. If it divides 15 and 12, it must also divide the 3. Well, there you are, and if it divides the 3, then it must be smaller than 3 or equal to 3, which means 3 must be the greatest number that divides into them all. That's why you can say the greatest common divisor of 195 and 42 is 3. 3 can be rearranged into 15 take away 1 times 12. Move up a line. The 12 can be rearranged into 27 minus 1 times 15. So now you can combine them. That's plus 1 times 15. So now I've got 2 times 15 minus 1 times 27. Move up. That 15 can be rearranged into 42 minus 1 times 27, minus the 1 times 27 we've got already. So that would be 2 times 42 minus 2 in another one, minus 3 times 27. Move it back up another one. So I've got 2 times 42 minus 3 times, and that's 195 minus 4 times 42. So altogether that's going to be 12, and the 2 makes 14 lots of 42 minus 3 times 195, and that's equal to 3. That's the Euclidean algorithm served its purpose in arriving at these two figures. So back up to the top. Now just rearrange that into the form of that equation, which has got the 195 first. So 195 times negative 3 plus 42 times 14 equals 3. However, this equals 12, so multiply it all by 4. So 195 times negative 12 plus 42 times multiplying by 4, 56, equals 12, which you can check in your calculator. Now that's just two particular numbers. It said what's the closest values of x and y, meaning really what's the smallest integer values, not meaning the smallest integer value being like negative several million, but closest to 0. Well, you can alter this equation. That's just one solution. Negative 12 works, and 56 works. Well, since I've got two parts, if I was to add 42 onto this, that would add an extra 42 times 195 to all of this side, which you can do if you like, as long as you take it away again. And I can take it away here. If I take away 42 times 195, then I've got 42 times 195 added on, and 42 times 195 subtracted. That still balances, but now I've got two new numbers. In fact, if I left myself more room, I could add on as many 42s as I like to this one, as long as I subtract the same number of 195s from this one. So I could rewrite that as n 42 plus 42 times 56 minus n 195 equals 12, where n is an integer. More than that, because the greatest divisor of the two numbers was 3, you can divide both of them by 3 to get smaller increments that would still be true, and that would be the general solution then. The general solution to that Diophantine equation would be x equals negative 12 plus 3 into 42 goes 14n, y equals 56 minus 3 into 195, 65n, where n is an integer. So to get the smallest numbers then, to get the values of x and y that are closest together, you just choose n accordingly. Well, choosing n equals positive 1. So if n equals 1, I'll have x equals negative 12 plus 14, which is 2, that's pretty small, and y equals 56, take away 65, which will be negative 9. So the two smallest integers that solve this Diophantine equation are 2 and negative 9, which you can check in your calculator.